Sushant Sharma is a BTech graduate in Computer Science and Engineering from IIT Guwahati. He has a rich experience of over 15 years as an IT professional working with well-known organizations as CATS Private Limited, TCS, Tech Mahindra, and Romeware. After his meeting with Dr. T.D. Singh in 2000, he developed a keen interest in the domain of synthesis of science and spirituality. Under the mentorship of Dr. T.D. Singh and his students, Sushant has been exploring the studies at the interface of foundations of computer science, mathematics, and consciousness, and consequently has been delivering many talks in various organizations, conferences, seminars, and workshops organized by Bhaktivedanta Institute. His study interests include foundations of set theory and computer science, Gödel's incompleteness theorems, and Vedanta. Currently, he is working in Nevai Technologies, besides undertaking the responsibility of being the Director of Cognitive Studies and Fine Arts of Bhaktivedanta Institutes.
Welcome everyone. I'm pretty sure you must be enjoying this wonderful summer school with a wonderful theme, namely information. We are living in a world of information, not presently, but since eternity. And information is abundant in this universe. However, there is one difference that I should make you aware of, the difference between data and information. So we have got data, and so much data is there, and but these data are not unstructured. There are patterns, the patterns which are observed some of the cases, and in most of the cases still the mathematicians and scientists, they are trying to observe the patterns across these data. So these patterns is what form a very important limb information. So we can say the patterns are informations. Informations can be the patterns, the very formulae with which the data have been bound. So which means the information itself, the pattern itself is another data. So the data is not just scattered here and there like this. There are patterns, there are structures which are governing the existence of the data. And these patterns can be simple, these patterns can be complex. And many mathematicians, they have been trying to understand the source of these patterns. They have also been trying to understand, they have been trying to ask themselves, will it be possible that if we are able to ferret out all these patterns, or at least prove the existence of these patterns information. So keeping that in mind, I have made this humble slideshow from complexity to divinity. What you are observing in this right hand side of this slide is a medal which was given to Chaitin. Most of the work here in these slides will be a tribute to Chaitin, uh, Grigory Chaitin. And you can see the omega. The omega is the one which is a very mysterious number, a new number, having been identified, having been discovered by Chaitin himself. These slides are dedicated to my mentor, my spiritual master, Dr. T.D. Singh, His Holiness Bhakti Swarup Damodar Maharaj Ji. You know, the computability is, we can say the computability is the mechanism, is the route that the programmers or the mathematicians, they undertake to ferret out the patterns, the information which is threading the data together. And there have been many computation model presented by one or other mathematicians. So here I have presented to you the Mount Rushmore of computability. Like we have this Mount Rushmore in USA. A very big hill has been carved into some 4 or 5 So these great mathematicians and logicians, they have proposed wonderful things in the world of mathematics, especially computation, starting with Cantor and Hilbert, Gödel, and ultimately Turing, and definitely the descendants of Turing, namely Chaitin and wonderful Newman and Kogomorov. So all these wonderful computer scientists or formal mathematicians, they have uh, over the years, uh, laid out the foundation of the present computers. Uh, though it was completely a prototype made by Turing, but the these great mathematicians also, their ideas also have been incorporated. So, for example, Cantor, he proposed the set theory, and he also proposed the concept of infinity, where he says Cantor is recognized as the founder of set theory, and the concept of infinity, I am writing new concept of infinity because before Cantor it was understood that there is only one infinity. The Cantor came and told actually there are infinite infinities. And Cantor also proposed a wonderful method of diagonalization, which is proved or which is used to prove or disprove many theorems, actually, including the Gödel's incompleteness theorem. Hilbert, Hilbert in his time was considered to be the greatest mathematician, and he proposed uh, something called as Hilbert program, wherein he wanted all the true statements to be proved. He was like looking forward to this idea that will it be possible to come up with a mathematical structure, a formal mathematical structure, formal mathematical system. We can also say formal proof system which can prove all the true statements. I mean, uh, there are many statements, and it should be, the system should be sufficiently potent enough to prove or disprove the statements within that system. So Gödel, the greatest logician of the 21st century, he came up with his famous incompleteness theorem to tell Hilbert and all of us that actually it is a wishful thinking. We can never have a formal axiomatic uh, mathematical system you know, which can prove all the true statements in the system itself. That is called as incompleteness theorem. He's saying that that system, the mathematical system, will always remain incomplete. So I will not go in detail into Gödel, but what is interesting is Turing. The Turing, he proposed a Turing machine, which is actually nothing else but the prototype of modern day computer. So we can say Turing is the father of modern day computers, actually. And Turing, he also, coined this term, the halting problem. The halting problem is very interesting. In fact, this is another flavor of incompleteness theorem proposed by Gödel himself. Some people say, including Chaitin, that actually the root of incompleteness theorem proposed by Gödel is in the halting problem. So halting problem is actually more foundational. So what is halting problem? So these two together, Gödel and Turing together, they gave a little bit of setback, huge setback to Hilbert. They kind of shook the entire mathematical ideas they were having. The foundation of mathematics itself was shaken by these two stalwarts, namely Gödel and Turing. uh, can I just ask you to confirm me that if I'm audible the last time, please?
Yes, sir. You are audible.
Very good, thank you. So Turing came with this idea of computability, wherein he proposed this Turing machine, which is essentially an infinite tape, and this tape is having these bits. zeros and ones. What are these bits? Actually, this is a binary representation of the algorithm of the program. You know, the algorithm, the program, any program, let's say, if you want to find the square of 2, so how will we do it? We'll just multiply 2 by 2. If you want to find the square of x, we'll multiply x by x. And how will you realize multiplication itself? We will multiplication is addition that many number of times. So all these instructions, they are strings, and they can actually be represented in the form of binary strings, zeros and ones. You know, this x plus the very symbols x plus is equal to, everything can be denoted by one binary representation. And so therefore, not only the symbols, but the whole programs themselves can be represented in the form of binary strings. And the tape is having the binary string, and it is moving left and right, and there is this particular reader here. This reader is actually um, looking at the current symbol, and it's judging what the next move is going to be, whether I should move the tape left or right. So this is this is very much the prototype of present day computers. um, the end users, people who are actually using the computer, almost everyone uses a computer or mobile, everything. They may not be aware of this, but the computer architecture people, and they know that in behind the scene there are so many things happening involving memory, the CPU, the ALU, microprocessor, and so many structure, so many artifacts are there. Believe me, they are nothing else but the manifestation, the modern day manifestation of what Turing presented years back. So Turing is very important, Alan Turing, and he is very rightly called as the father of modern computer science as well as computers also. So don't get carried away, don't get intimidated by these uh, intimidating pictures. Just try to understand the spirit behind these great ideas actually. So Turing also proposed that if there is a Turing machine, then there has to be a universal Turing machine also. So Turing machine is essentially, so let's say every program is a Turing machine. Every program will have a Turing machine. You find the square root of a number, you find the cube root of a number, you want to prove something, or so there are millions and millions of programs, and therefore you can have millions and millions and countless Turing machines, one for each program. So the Turing machine will be, it's a machine, and some input is fed and some output is coming. The beauty of this whole concept of Turing machine as given by Turing himself is that the whole Turing machine itself can be represented in the form of binary string, which I already told you. Not only the input and output are the binary strings, but the Turing machine itself can be broken down into binary strings. In computers, when we are running the programs, as the program is actually loaded in the memory, including our operating system, Android and so. So loaded in the memory means they are loaded in the form of this binary representation, 0 and 1. So there can be a universal Turing machine, which in the case of universal Turing machine, now the input here to the universal Turing machine will be the Turing machine itself, and the output will be depending. So therefore, on our computer, we can run thousands of applications, actually thousands of programs, can't we? On our mobile, we can run thousands of applications. Uh, so Turing proposed that there can be a universal Turing machine. The input of that universal Turing machine will be an individual Turing machine, and the output will be the same as given by the Turing machine itself. Now, this is a wonderful question that Turing proposed as a food for thought, that will T halt, I mean, T halt, what is the meaning of halt? Halt will it stop for every input with a definite output? This is a famous halting problem. So our universal Turing machine, it is the job of the universal Turing machine to judge whether a particular Turing machine will halt or not every time. So, so Turing in 1936 proved that it is impossible to construct such a machine which will deterministically and decisively tell whether a particular Turing machine halts or not. I'll just give you an example. For example, here you are seeing this algorithm, the flow chart for finding out whether a number is prime or not, uh, if a number is prime number or not. So you can have a flow chart like this, and if you introduce, so this flow chart means this is a Turing machine. If there is a flow chart, there has to be a Turing machine for this is prime. So the input of this prime number algorithm is the number itself, and the output is true or false. Now this Turing machine can be fed into the universal Turing machine. The universal Turing machine will say, yes, this will halt. This will definitely halt. The universal Turing machine will tell us. Okay, these are all thought experiments, huh? Thought ideas. Whereas look at this flow chart on the right hand side, where it is an infinite loop which will never be broken. So essentially this will never be broken. So which means that this will actually never halt. The good thing is that the universal Turing machine will still be able to deduce that this will not halt deterministically. Very decisively, it will be able to tell that the left algorithm will halt and the right one will not halt. So, in this way, it can prove or disprove. However, there are certain algorithms which are really very evasive, and that's where the beauty peeps in. And that one are, the examples of many conjecture. Goldbach's conjecture is considered to be a very famous example of such algorithm. So what does Goldbach's conjecture say? It says that every even number is a sum of two primes. For example, take any even number. For example, 16. 16 is a sum of 13 and 3. It says that any even number can be represented as a sum of two prime. It says that you take any even number, there must be somewhere two prime numbers. When we add those two prime numbers, the result will be this even number. So this is a conjecture, and they have seen that it is true. They have seen that it is true for very large number, billions of numbers. They have actually uh, found it out that actually it is true, which means for every number they have been able to find out that yes, there exists a pair of such prime numbers. But that does not mean that in the future there will not be a number, an even number, for which this conjecture does not hold true. Just because you have been with specification, you have treating each and every number, you have been able to prove it. That does not mean that you have been able to prove for all the numbers. uh, you know I'm pretty sure you must all have gone through this subject of mathematical induction in your school days. With using the induction, we used to prove that something is true or false for if something is true for n, and if we can prove that it will be true for n plus 1 also, then in this way using the mathematical induction, we prove that it will be true for all natural numbers. But however, Goldbach's conjecture and many such conjectures are special in such a way that the induction simply does not help. It You have been able to prove it for some number, let's say n. With that, you cannot proceed to your proof with n plus 1th number. And the algorithm for this Goldbach's conjecture is very simple actually. This flowchart is very simple. You take, what is the input of this? Input is an even integer and output is a pair of prime numbers such that n is equal to p1 plus p2. Actually, we can define our own output. We can define the secondary output to be true or false. So if we are able to find a pair of prime numbers like this, we'll say it holds. It is true. The conjecture is true. At the moment we are able to find out an even number for which we are not able to find any pair of prime numbers, that very moment the conjecture will be proven to be false. So now if we on the right hand side is the UTM, the universal Turing machine, and GCA is a Goldbach conjecture algorithm which we saw in this slide here. This algorithm, since this is an algorithm, there has to be a Turing machine for this. We are, as a routine, passing that Turing machine to the universal Turing machine, and now the universal Turing machine is asked to prove whether this GCA will halt or not, and that's where UTM will be, caught in a loop itself. It will not be able to deduce whether Goldbach's conjecture algorithm is true or false. So this is a halting problem. This is a halting problem. So what we can say that UTM is not computable. Moving ahead, Kolmogorov in the present times and in 60s, I think, he came up with this concept of algorithmic complexity, or which can also be called a descriptive complexity. What is it? It measures the complexity of an object, such as a string, by the length of the shortest possible program in a fixed programming languages that produces the object as output. For example, look at this. The very simple example, we have this pattern A. There are 6 A's. Okay, so so there is a pattern. So there is this data is there, and this data is there, and there is an information there, and this information is actually a very simple information. You can just write like this: 6 A's. Or if suppose if you had trillions of A's, you'll be writing it trillion A's. So this is the complexity of this. It measures the complexity of an object by the length of the shortest possible program. This is the shortest program, just to give you an idea. However, if you take this string like this string 7DG85NF93, you're seeing that there is not a pattern. There is no pattern here. So we cannot break down this whole information or whole data in the form of some simpler algorithm. So how do we then describe this? There is only one way to describe it, and that one way is the description itself. I mean, uh, we say we have to say the whole thing, 7DG85NF93. So we say that the second example, this sequence is having more complexity than the first one. And the higher the complexity is, the more random the object is called to be. So the second example here in this case is more random, whereas the above one is not random. It is computable and it is lesser random. We'll take some more example. For example, these two patterns are there, and so the idea behind measuring the complexity is to judge which one is more complex and which one is random. So, so, so now when we look at it at the first glance, both of them seem like having very complex pattern. In fact, they look random, absolutely random to us. But actually, this is interesting because, the first sequence, this sequence, the one in green, is actually very easy to describe. What is this first sequence? you can read in the bottom. It is a digits 49th to 607th of pi, which are less than 7 and greater than 0. So which means ये हमने जितना भी whatever is written here in this green can be described into few words like this. The digits 49 to 607th of pi, which are less than 7 and greater than 0. In English, it can be described like this, and there can be also even simpler programming language description like you are seeing here. Select real digits pi and all those things, some select statement. Whereas a one in blue, it is from this site random.org. It is random, and it is random, and so therefore it is more complex. Because it is more complex, it is more random. In fact, uh, there is no pattern there here. So this complexity is actually very important. Like, for example, I understand in the case of the theory of information, in the information theory, I'm pretty sure some of the speaker must have talked about it, or maybe they will talk about it, that this complexity of information is a very critical idea, is a very critical element. So in the case of algorithmic information theory, where the algorithm itself is an information, we should here also talk about the complexity of the algorithm. And the complexity is defined. I'll just let me take you to the definition slide. The complexity is defined as the length of the shortest possible program that produces the object as output. This complexity is called as algorithmic complexity. It is also called as Kolmogorov complexity, because Kolmogorov is the one who actually proposed this. And it is also called a descriptive complexity because it is the shortest description. Okay, I hope this must be clear. So, and another example is this Mandelbrot set, which is actually in terms of its what do you call consumption of data bytes or bits. It's really very complex. It is here actually it is taking around millions of bits, but it actually its descriptive complexity is actually very low, because this Mandelbrot set can actually be represented by very easy, simple formulae. All right, so so now this is beautiful. They have come up with this theorem kind of thing, that there does not exist any algorithm to calculate the complexity of any bit sequence. Like, so, you know, so it is again a thought machine. We want to have a generalized machine, and the input of that generalized machine will be this sequence, any sequence, and the output will be to calculate the complexity. So the idea is that no such algorithm, no such machine will exist. They have actually proven it using Berry paradox. Now comes a wonderful, mysterious, godly number, omega. Omega is a real number that represents the halting probability of a universal prefix Turing machine. So what is a prefix Turing machine? You know, every machine can be represented in the form of binary string, and should not happen that one machine is a prefix of another machine, which means one binary representation should not be a prefix in another binary representation. Are you understand? So if there are two Turing machines and they have got their individual binary representation in zeros and one, and if we find out that the binary representation of Turing machine 1 is there as a prefix in the binary representation of Turing machine number 2, then that will not be called as a prefix-free Turing machine. In the case of prefix-free Turing machine, universal prefix-free Turing machine, their Chaitin proposed that we can actually measure the halting probability, whether the Turing machine will halt or not. So this concept was proposed by Grigory Chaitin. And actually, in one of our volumes of Savigyanam, our journal, Journal of Bhaktivedanta Institute, we can find a wonderful article by Chaitin where he actually has introduced this concept of omega. Okay, so it captures the idea of randomness in the halting problem and provides insights into algorithmic information theory. So how is it mentioned? How is it calculated actually? Or how is it defined rather, I will say. So, you know, as I said, you can have the binary representation of the all the machines. So let's say this let's say if you are having only one bit necessary, one, the machines consume only one bit. In this case, the omega 1 is described as 0. In the case of if you use 2 bits to represent your Turing machines, then there will be 4 such combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And out of this 4 combination, only one will halt, only one will halt, let's say. So this is all thought experiment. So you can define omega 2, which means omega and 2 is the number of bits, that is 1 by 4. So the probability of the halting is 1 by 4, because it is 1 among 4. Similarly, omega 3 is 3 by 8 because there are 8, but only 3 will halt. Omega 4, omega 5. So in the case of universal Turing machine, you know how many bits will be there? There will be actually infinite bits. So because there can be definitely machines with all kind of sequences, infinite sequences. So how do we define? So we have got this individual omega 1, omega 2, omega 3. So we can then put a limit, limit where omega I is defined as sigma of 2 to the power minus p halts. Why? Because I'll just see what is 32 here. 32 is actually 2 to the power 5, right? 2 to the power 5 is 32. And out of those 32 sequences, only 22, 22 will halt. So sigma of 2 to the power minus p means 1 plus 1 plus 1, so 22 by 32. 1 by 32 plus 1 by 32 plus 1 by 32. Uh, so here 1 represents uh, every case where the machine actually halts. So we can put a limit, omega I is equal to sigma of 2 to the power minus 2 to the power minus I, where p halts. So we can say limit I tends to infinity. That is a very huge number. But the thing is that this number, even though it is huge in terms of uh, digits, but actually it is still a fraction. You see, the 22 by 32 is still less than 1. All these numbers, omegas, are less than 1. So there is, which means that this number does converge to something lesser than something between 0 and 1. So there, it is therefore we say it's a halting probability. There are bounds, lower and upper bounds of this. So omega, so this way we have defined omega. This way Chaitin defined omega, but there is beautiful caveat here. The caveat is the Chaitin omega is both random and uncomputable. Which means what? So there are, you must have understood that there are all these set of numbers. We have integers and we have got rationals. We have got constructibles like root 2. What are constructible numbers? Those numbers which can be actually realize using a simple compass and headset. How will you realize root 2 using a simple compass or headset? You just draw a triangle, the triangle with side 1 and 1, right triangle. Right triangle? Yes, right triangle. Uh, so what will be the length of the hypotenuse? It will be root 2. So using just simple ruler, heads, we call it hedge set, you can actually construct these numbers. However, there are some numbers which you cannot construct using, but they are still algebraic. For example, cube root of 2. So square root of 2 is constructible, whereas cube root of 2 is not constructible, but it is algebraic because, it exists. We can have polynomials of surrounding that cube root. Then we have got computable numbers like pi. Pi is a computable number, which means you can actually write a program to compute this number. That's a separate thing, that this program will never halt. But still, the program is the program. And sigma or something in E is famous. These numbers are really very, very kind of important numbers, pi, E, and all these numbers. But omega, proposed by Chaitin, has made its entry into another mysterious number, but omega is so mysterious that it is definable but not computable. It is definable. We have defined it this way. We have defined it. It is definable, but it is not computable, which means we cannot have an algorithm for this. It is so random. It is so very. The words random and computability should not be mixed. There can be random. Uh, there can be random numbers which are computable. Can anyone give me an example? Okay, I'll only give the example. Pi itself, pi is random. The sequence in pi is random, but it is computable. Same is E. And we have got this random number generator also. Random number generator. Uh, it's an algorithm in itself. It produces random numbers. But omega is not only random, it is uncomputable also. So Chaitin will say that omega is a mysterious number. It's I will finish it in 5 minutes. Omega is an unknown number. It's an unknown. It is here very much around us, but it is an unknown number. And see how Chaitin connects this concept of omega to divinity in a very beautiful way, and I'm pretty sure you will appreciate his quotes, which I'm going to share in the next slide. Here he says, Chaitin says, uh, I'll read it out. Does that number omega exist? It exists in the mind of God. To an infinite mind, it is knowable. You could calculate each bit, but we are not infinite minds, right? You can argue that it does not even exist, that it's a fantasy object. Mathematically, it does not use very sophisticated math. There is much wilder mathematics, but the numerical value of this number omega is maximally unstructured and maximally unknowable. So compared to the kinds of things you do normal in mathematics, this is a forever unknowable thing. The value of each individual bit in the numerical value of this number. So Chaitin is saying that this number is actually a divine number. It exists, but it is unknowable to us, but not unknowable to God. Because ultimately all this data information, they have actually all been patternized by some creator according to the definition of God. We can define God like this. We can simply define God as one who knows the sequence of pi completely. We can define God as one who knows omega. He's saying, Chaitin is saying that for us, it will be a forever unknowable thing. But for God, it is like another number in his basket. Another beautiful quote by Chaitin is, the creation is a coding. He says, so saying that the universe is built out of information is like saying that the universe is really built out of spirit, or the universe is in the mind of God. It's not a material object. So the information, the theme of this summer school is information. The information is a gesture of the informer, God. Coder, information is the coding, God is the coder. Chaitin is saying, I'm just sharing the words of Chaitin. And he says that the universe is really built out of the spirit. So this spirit in the mind of God is what we see as information and the data, and that how the data is, all the data threaded with one another in so many patterns in a very mysterious way. So if Chaitin can, transcend from the information theory to algorithmic information theory to Omega to Divinity, so we can also do it. As I start, thank you so very much for paying attention to my slides. I'll stop here now.